Stripping down science. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also here this week is Kat Arney. Hi, Kat.
Hello.
Now, find out this week how scientists have discovered the most powerful tongue in the world. Unsurprisingly, it doesn't belong to my mother-in-law. But whose is it? Well, we'll be finding out shortly. Also, how can aspirin cut cancer rates? Can it? And can it do it as well as it cuts our risk of having a heart attack? And also, a wacky way to ward off global warming. A US scientist wants to mine the moon for materials to make a cloud that can give the Earth some shade from the sun. That's all on the way. Kat.
Also this week, we're exploring the world of radioactivity, including finding out how a nuclear power station works. Earlier in the week, we sent off Dave and Anna to Sizewell B in Suffolk. You can hear how they got on later, and they didn't come back glowing like the Ready Beck kids. We'll also be joined by Cambridge University's Ian Farnan to look into the thorny issue of what we actually do with the world's nuclear waste. How should we store it, and what should we do with it? In Kitchen Science, we'll be doing our own bit of radioactive research, discovering how a smoke detector works. Plus, Anant Krishnan's here from Addenbrooke's Hospital to explain how radioactivity can help doctors to diagnose and treat disease.
And if you're in the mood to win something, then there's a copy of my new book up for grabs. It's called Naked Science, and it's full of all the fun and funky science discoveries that we talk about here on The Naked Scientists. And I'm going to give away a copy which has been signed by me to a lucky winner this week. So for a chance to win that, have a go at this question. What nuclear process powers the sun?
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, who has got the world's most powerful tongue? Well, it used to be a toad called the giant Colorado river toad. Its Latin name was Bufo alvarius, but unfortunately his throne has been usurped this week, Kat, by the new holder of this amazing title.
Is it me? Look at this. Have you seen this? Look.
Actually, I think that's not as big as my wife's tongue. Actually, she has got an incredibly big tongue. I'd have to say, she won't stick it out for me anymore because I keep taking the rip out of it every time I see it. But no, the fastest and most powerful tongue in the world is owned by the giant palm salamander, and this crawls around on the forest floor of Central America. And the reason it's got such a fast tongue is because it needs to catch flies and things like that, and it does that by lashing out its tongue very, very quickly. It's been studied by a guy called Stephen Debon, who's from the University of South Florida, and it packs an incredible 18 kilowatts per kilogram punch, which is twice the power of the toad's tongue. It's an incredibly powerful piece of muscle, but things don't quite add up, because what the team did is to use a video camera to take very fast action pictures of this tongue flicking out, and what they found was that it's moving much faster than it would do just on the basis of muscle power alone. So what's going on? Well, they then attached some electrodes to the surface of the tongue to work out what the muscle cells were doing electrically at the time when the tongue was moving. And what they found was that the tongue moves for longer than the muscles are actually active for. So it's actually storing up energy somewhere. So they went inside the tongue for a look, and what you've got are muscle cells, and they've got these bands, like elastic bands of the tissue collagen wrapped around them in a sort of plait. And what the tongue does is to store energy locked away inside that collagen, like a big, long, stretched elastic band. And then when this animal deploys its tongue, literally the collagen snaps back like a bowstring, and the tongue goes flying out much faster than you would do just if you powered it with muscles.
Absolutely crazy. I'm sure there's some use for that somewhere. Anyway, we're talking about the anti-cancer properties of aspirin. Humble aspirin is a bit of a wonder drug.
It is, isn't it? 1950, Guinness Book of Records, world's most popular painkiller.
It's incredible.
50,000 tonnes a year got sunk in that year.
Just you?
Not me. My wife is a headache. My mother-in-law's an even bigger headache, but not that big a headache. You'd have a very big ulcer if you swallowed that much aspirin.
But anyway, some research has previously shown that aspirin can actually help to prevent certain types of cancer, for example, bowel cancer, and it's also good for things like heart disease as well. And so now Cancer Research UK has opened a clinical trial to test whether humble aspirin can actually prevent esophageal cancer. That's cancer of your gullet, your food pipe. And this type of cancer is on the rise in the UK. We've got one of the highest rates of the disease in Europe.
Do we know why?
And it's partly to do with obesity. So the bigger you are, the more likely you are to have acid coming back from your stomach into the bottom of your gullet, which can cause this. Eating a lot of rich and fatty foods and drinking alcohol is also a really good culprit, and aspirins are terrible for that.
So other countries that have a diet similar to ours, a weight problem like ours, I'm thinking, say, the US and Australia, do they have similar rates of esophageal cancer like us?
They do have high rates. They're not actually quite as high as us, so there may be other things at play. But what we're trying to do is actually find out if you can prevent the development of esophageal cancer. So there's a trial that's recruiting at the moment. They're looking for 5,000 men and women who have a condition called Barrett's esophagus. And this is a condition you get at the bottom of your food pipe when stomach acid comes back up and it affects the cells there. And in fact, having Barrett's esophagus does make you 50 times more likely to develop cancer of the esophagus. So they're running a trial which is called ASPECT to test whether a combination of aspirin and an acid-blocking anti-ulcer drug called esomeprazole can prevent esophageal cancer from developing. It's quite a long-term study, and I think it might work by damping down acid production and also getting rid of the long-term low-level inflammation that might lead to cancer. So actually the ASPECT trial team are looking for people who have Barrett's esophagus who want to take part in the trial. And if that's for you and you live in the UK, the best way to find out more is to ask your GP or call the Cancer Research UK nurse team on 0207 061 8355, or you can go and look at the charity's patient website, which is www.cancerhelp.org.uk.
Aspirin does seem to have a lot of interesting effects beyond just its ability to reduce the risk of heart disease, doesn't it? Why does it, we think, reduce the risk of all of these cancers and Alzheimer's disease too?
It's, in terms of cancer, it's probably to do, as I said, with inflammation. There's a growing idea that cancer, in some cases at least, might be caused by very long-term, low-level inflammation or inflammatory molecules, and maybe aspirin's working in some way to damp these down and may prevent cancer. There's quite strong evidence for it in things like bowel cancer.
Well, certainly food for thought, so if you want to have a go at that, then we'll have the details of that on our website, nakedscientist.com, when we put all the content from this show there later in the week, so you can catch up with details of how to join that trial if you're interested. Now, an interesting and rather wacky suggestion about how we might combat the problem of global warming now. It's been published in the Journal of British and Interplanetary Science, and it's a US scientist called Curtis Struck, who's at the Iowa State University. What he's suggesting is that one way to cut down the problem of global warming is to put a big dust cloud in space, which would orbit the Earth in the same way that the Moon does, and once a month it would come directly between the Sun and the Earth, block out the Sun's rays to the Earth, and therefore the supply of heat to the Earth, and would therefore cool the planet down. Where do we get this dust from? Well, what he's suggesting is that you need dust that's about 1 micron or 1,000th of a millimetre across, so very, very tiny. The Moon's surface is the perfect source of this. So mine the Moon, get loads of this dust, and then produce this very big set of clouds, which would be positioned at what's known as a Lagrange point. And these are stable gravitational points. And if you can imagine an equilateral triangle, and it's got the Moon at one of the corners, the Earth at the other, you'd put this cloud on the other corner, where the Moon goes around the Earth. And so this cloud would orbit stably and therefore block out the sun's rays periodically. Critics of the idea, Kat, suggest that it might be a bit of a bad idea because it may paradoxically act like a tiny mirror when it's not directly between the sun and the Earth, and this would reflect more heat onto the Earth and might actually warm us up. Although Curtis Struck says, in fact, if you do the sums, then no, it doesn't add up. It probably would still create a sort of a dampening down and a reduction in heat supply to the Earth. The other major problem is that this would create the equivalent of a full moon, but on a massive scale, so it would massively and dramatically increase the amount of light at night time. We don't know what the consequences of that would be, but we know that during night time, lots of plants and animals are adapted to having darkness and light, and they have a body clock, and this kind of level of light could seriously screw around with that and may have a very big, unforeseen and dramatic environmental impact.
I think I'll just be trying to use my car a bit less rather than going and mining for moon dust. Anyway, research presented at a scientific conference in the States has suggested that protein analysis could actually be used to predict who's at risk of giving birth prematurely. Researchers have been studying the inflammation proteins that are found in amniotic fluid. This is the liquid that surrounds a baby in a womb. Now, signs of inflammation are found in around half of all women who give birth prematurely. And there's loads and loads of proteins that are found in amniotic fluid, but not all of them are actually meaningful for medical diagnosis. But what the team have done is studied amniotic fluid that's taken from 120 women who'd gone into hospital for a premature birth, and they looked at certain proteins, and they've basically defined a set of proteins that are really good indicators of infection and inflammation in the placenta and the umbilical cord, and that makes a woman more likely to give birth prematurely. And now it's only a small study at the moment, so the next step is to try and do a larger trial of this. But it could be a way of finding ways to predict which mums and babies are at risk of premature birth and then subsequent infection. And then you could monitor them and treat them.
Having an amniocentesis isn't without risks, is it?
It's not, no. It is a risky procedure.
1% risk of miscarriage in people who have it.
But then again, having a very premature birth or having an infection in a baby after birth is also a risk. It's a balance of risks and benefits.
So if you're having one anyway, you're saying that they could subject this to this other panel of tests and therefore you'd know to be warned?
Exactly. It's a reliable, they think, a reliable way of predicting who's at risk of infection.
It's The Naked Scientist with Dr. Chris and Dr. Kat. We've got a radiation-centric show this evening. We'll be heading off soon to Sizewell B Nuclear Power Station, where Anna and Dave have been finding out how it actually works. We'll also be finding out how a smoke detector works, and then finding out what we can do with all of the country's nuclear waste from Ian Farnan, and then also exploring the science of medicine as it relates to radiation and radiology. What can radiation do for medicine and help doctors to make patients better and to make better diagnoses?
The Naked Scientists, supported by the Wellcome Trust.
Now, Kat, I've got a great question here for you. It's from Jessica, who's actually listening in South Carolina. She says, love the show. I actually listen on the iPod on my commute to work. I've got a genetics question for you, which I hope will fit with what you're talking about. My husband is colourblind, and we recently had a baby girl. I know that colourblindness is an X-linked recessive trait. In other words, it's on the X chromosome, and that one X chromosome is randomly switched off in females, because females, of course, have two X chromosomes and they randomly turn off one of them because they only need one. That's why men can get away with having one. Does this mean that our daughter, as a carrier, could be colourblind in one eye or some of her cone cells, but not all of them? What do you think, Kat?
Well, the answer is that your daughter is a mosaic, as all women are. And I don't mean that we're made of little tiny bits of ceramic pottery, but because we have two X chromosomes as women, one of them gets switched off in every cell, and this is usually, in healthy people, a completely random process. So colourblindness is when there's a faulty gene on one of the X chromosomes, and if you're a man, you don't have a counterbalance to that, so you will have the problem. Whereas if you're a woman and one of your X chromosomes is dodgy, it may be switched off in some cells, it may be on in some cells, but the mixture, the healthy cells are going to compensate for that. So you're not going to be colourblind in just one eye. Some of your cells will have the colourblindness problem, but there's enough healthy ones to compensate.
There are actually multiple copies of the pigment that enables you to see red, aren't there? On the X gene, the X chromosome has this gene for being able to see red, and I think there are multiple versions of that gene, and so you can end up with some women who have inherited one copy from one parent, which is one version of the gene, and another version from another parent. Because this random process you've just been talking about takes place, you end up with this mosaic pattern on your retina, as you say, and some bits of the eye see a slightly different colour red than other bits. And in fact, if you go across the retina with a laser at a certain wavelength, you would be able to ask people, what do you see? And they would say you were shining lights of slightly different colours across their eye as you scanned across the retina for that reason.
But because the brain integrates all this information so well, most of the time you would never even notice.
In fact, the person who described that process was a lady called Mary Lyon. Lyonisation, switching off the X chromosome. I believe that she came originally from Norwich, which is, of course, in this region.
Yeah, she was an amazing scientist. Anyway, I've got a question for you, Chris, and this is something that's interested me. So, you're trying to go to sleep at night. This is a question from Aileen Campbell. Why do you start twitching? Why does your body jump when you're just trying to drop off to sleep?
Withdrawal symptoms from the Naked Scientist, perhaps.
Obviously.
No, I get this. Have you ever had this when you're just dropping off, or when your partner's just dropping off and then they suddenly jerk convulsively and you wonder what's going on with them? But this is called a hypnic jerk. Hypnosis and sleep. And the reason that we think it happens is that when you go to sleep, your body's completely paralysed. And the reason for that is that when you dream, you don't want to be acting out your dreams, because otherwise that could get nasty. Because, well, in my case it could. The manifestation you all have known about with this is you must have had a dream where someone's chasing you, and you get that horrible feeling of running through treacle. You feel really weak and you can't get away, and that's because you are literally paralysed in your sleep. But the process of that paralysis kicking in occasionally causes these funny jerks, these dropping off to sleep jerks, and they are referred to as hypnic jerks. People have done experiments on cats where they know which bit of the brain, it's called the subcerulear region, is involved in this paralysis process, and they've temporarily turned that bit of their brain off, and you get cats prancing around acting out these dreams that they're having and prancing imaginary prey. Stalking imaginary prey. So it can be done. Now, this is interesting because last week we had a question to the programme which was all about why it is that ice forms on one part of a car and on another. Alan in Huntingdon wrote in with this question. We've got a little clip of it because we weren't sure the answer, and this is what Phil had on the programme.
We've also got a question here, and actually, to be honest, I'm struggling with the answer a little bit. It says, I enjoy your show on Cambridge Wireless. Here's the question. Why is it that car front windscreens appear more prone to icing than the sides and the rear? This is even when parked either way around relative to the prevailing wind, I think. Thank you, Alan from Huntington.
No, I don't know the answer to that. I think we're going to have to ask people to help us.
Well, we've had a couple of emails in. We have one from Dan Hoover in New Jersey who says he thinks that it's because over time you driving around and you get kind of little pitting in your front windscreen by dust, water, little bits of stones, and he thinks that this acts as a nucleation site for ice, so it's encouraging ice to form. We've also had another email here from Bill in Canada, in Victoria, and he says that he thinks that it's probably due to moisture at the front of the car, greater air circulation at the front and the back of the car, making for a greater differential of temperature and moisture at the front. He thinks that's why it's more likely to freeze up.
Well, I think they're both on the right lines, but then I was pretty impressed to get a call this week from Professor Thomas Koop, who's from Bielefeld University in Germany. And in fact, I asked him if he'd mind if we recorded the conversation, and this is the answer, according to him.
Ice is more likely to form on front windscreens because they cool more quickly and to lower temperatures than the side windows of a car. Now, frost normally forms during nights that are clear and calm, and under such conditions, the ground and trees and any objects cool mainly by a process called radiative cooling. That is, they emit energy in the form of infrared radiation. The same happens to the front and side windows of your car, so they cool by emitting infrared radiation. But the side windows cool more slowly because what they do is, since they are vertically, they can pick up some of the radiation that is emitted by nearby trees and houses and the ground. So they receive some of that energy and thereby they cool more slowly. The front windows, in contrast, are directly pointed at the clear, cold sky, and therefore they receive very little infrared radiation from other objects and cool more quickly. And since they are cool more quickly, they are colder, and therefore frost is more likely to form on them.
It's Professor Thomas Koop, who's from Germany, and he actually rung me at 7 o'clock on Friday morning, in fact, Ken. My phone rang, and this person said, "Oh, is that the Naked Scientist?" And I said, yeah, it is actually, a very sleepy one. And he said, "Did I wake you up?" And I said, "No, it's all right, I just got up." But he said, "I think I know the answer to this question." So we made an arrangement to get together on Friday evening, and he had the answer. So thank you very much for that, Thomas. It is The Naked Scientist with Dr. Chris, Dr. Kat, and we're talking this week, in a couple of seconds, about the science of radiation and radioactivity. And then we're going to be exploring how a nuclear power station works, how a smoke detector works, coming up in just 2 ticks, and also finding out what we can do with the world's nuclear waste, and how radiation can be beneficial to medicine.
We're also running our teaser tonight. We want to know what nuclear process powers the sun. The rather spectacularly named Wurzel and Pauline in Dunwich are along the right lines. Also along the right lines, Andrew in Cambridge, Roger in Marsham, Pat in Sandham. Not quite there, I'm afraid, is it Jeff in Cambridge? So get calling in, 08459 25 2000, text us 07786 20 1960, and you can email Chris at nakedscientist.com.
Laying the facts bare, The Naked Scientists.
When was the last time you managed to cook some toast without setting the blinking thing off? I'm talking, of course, about a smoke detector. And this week, Dave Ansell and Anna Lacey got down to Dave's bedroom to find out about the science behind the radioactive source that could save your life. Hi there, guys.
Hi there. Yes, this week we're making a lot of noise. Oh, thank goodness it stopped. In Dave's bedroom, of all places. So, Dave, what is it that we're doing this week?
Having a look at how smoke alarms work.
So we're in Dave's bedroom, like I say, and I have to say it's more of a workshop than a bedroom. We've got soldering irons, clamps, and goodness knows what else in here. But Dave also got some stuff out here. This looks like a fire alarm that you've taken apart. Can you just describe what you've done there?
Well, this is just a normal smoke alarm which you'd have at home. I've just taken the first lid off it, the plastic lid, so we can see inside. What you can see here is you can see a loudspeaker, which is what makes the horrible noise we're hearing earlier, the battery which powers it, a few bits of electronics to run it all, and a rather ominous-looking silver cover. And inside there is where the actual detecting happens.
Okay, so what is it in there? And can we go inside?
We're going to have a look inside it, but first of all, this is something which you really, really shouldn't do at home. What's inside there is radioactive and could do you a lot of damage.
Okay, so what Dave's doing, he's just getting his tools and trying to take off the casing. Remember, this is not something you want to be doing at home because this is radiation, and radiation can be very, very dangerous indeed. So don't do this at home. And, okay, it's looking like it's nearly done there. Dave, can you give me some pointers about what's actually in there?
Well, we've revealed about 0.1 grams of americium. Now, this is a very heavy element, and the nucleus can lose a helium atom, which is 2 protons and 2 neutrons, and then that flies off at very high speed, and this is what we call an alpha particle. And I've got a Geiger counter sitting here so I know what's going on.
And a Geiger counter, that's kind of counting the alpha particles, is that right?
Yeah, every click you hear on a Geiger counter is actually some kind of radiation hitting it.
Should I be stepping back? Is this going to be dangerous for me to be standing near it?
It's actually stopped by about 4 or 5 centimetres of air, so as long as you're more than 4 centimetres away from it, it'll be fine.
Okay, right. So it might be quite good to hear what it's like, how many alpha particles are coming out. Whoa, okay.
What was coming off there, what was hitting the Geiger counter, was at least 2,000 alpha particles every second. So that's actually really quite a radioactive source.
But, Dave, we talked about this radiation so far, but, what does that do inside a smoke detector?
Well, inside the smoke alarm, there's 2 metal plates, and the electronics is attempting to pass an electric current through those metal plates. But because they're separated by air, which is a really good insulator, there's no charge in the air which can move, so no electric current can pass. So it's got a really high resistance.
So it's kind of like the circuit is broken because between these 2 plates there's some air and, you can't get a current just straight through the air like that.
Yeah, that's right. Now, if you put this americium in between the 2 plates, what you've got now is a load of alpha particles flying out. Those are charged. And when they hit air molecules, they knock electrons off. So you get free electrons, which can move around and carry charge. And you've got ions, positively charged ions, which can go in the other direction. So now you can actually pass a current through it, and the electronics will detect a current.
So all these extra electrons, they fill the gap?
Yeah, that's right. So this is what's happening normally. Now, if you put smoke into that gap, the little tiny smoke particles, which are too small for you to see, will actually mop up those electrons and those free ions, so reducing the number of free charges in there, so stopping the current, which electronics can detect, and then set off the alarm.
So the smoke's a little bit like a little sponge, and it's soaking up the electrons that were previously completing the circuit and making sure there's no alarm. And is it right that then the broken circuit equals alarm going off?
Yeah, that's right.
OK, so, that's the theory. Let's see it in action. Dave's got a candle here that he's going to light and a bit of dry leaf. So let's see it going. Got a bit of smoke coming up, up, up. Eesh. OK, there we go. Yes, the fire alarm's working. Dave's managed to put it all together very nicely and taken the battery apart.
So the smoke absorbed all those ions, increased the resistance, which the electronics could detect, and it set the alarm off.
OK, brilliant. And while I was seeing that smoking leaf there, it did just remind me that, of course, when I usually set up a smoke alarm, it's not when I've burnt my house down, but when I'm cooking things like sausages or bacon. They're not really on fire, so how come that seems to set off alarms?
Well, all you need in the alarm to set it off is a load of small particles, and if you burn sausages, that stuff which you can see as smoke is lots of small particles which will set off the alarm. Well,
that's absolutely fantastic. And of course, remember, don't open your own smoke detector, actually the actual radioactive source, because that's very dangerous. But do actually get yourself a smoke alarm if you don't have one in your house, because they can save lives every year, I'm sure. Well, thanks very much to Dave and Dave's bedroom stroke workshop. That's it for this week, and then we'll be back next week with some more kitchen science.
You can get arrested for burning those kind of leaves, Dave. That was Dave and Anna from The Naked Scientists, and they were finding out how a smoke detector works. Thank you very much, guys. Now, if you want to take part in next week's Kitchen Science, listen up, because we'll be doing some science in the dark. So what you'll need is a colourful magazine, say no more, access to a low-pressure sodium street lamp, so in other words, the ones that look nice and orange when you look at them, and not the ones that look white. It has to be an orangey colour, and we'll be telling you how you can do that next week.
Well, you've got a couple of emails here. Wayne in Ottawa says that he really wants to interest his grandchildren in science, loves the kitchen science. He wants to know if there's a summary somewhere of the experiments. I can't reveal exactly what, but keep checking out our website because all may be revealed. Also, another question on the website from Terry Waite, who says, I love the show, listen to it. It's not on long enough, in my opinion. They want to know, where can we get hold of
Is that the Terry Wade?
No, I don't think
When he
so.
says not on long enough, is that because he's in captivity?
Chris, you can't make those kind of jokes. Anyway, he wants to know, where can he get hold of your book, Naked Science, as he's not been lucky enough to win one? Well, the simple answer is just go to the Naked Scientist website, which is www.thenakedscientist.com. All sorts of stuff on there. You can buy the book and you can comment, you can go to the forum, so go and check it out.
Got an email here, Kat. I wonder if you can help me with this. It's actually from Bill. He says, I'm an engineer and an inventor. I love your show. I listen on the podcast, top notch. I've not missed a single version, and I love kitchen science. I have a rather large cast iron pan that I cook with, and it's developed a warp in the middle that makes the centre of the pan lower than the sides. This is not uncommon, obviously, for an older pan. My question is, why is it that when I put oil in the pan and then add heat, the oil heats up and defies gravity by travelling up the warp side of the pan away from the heat? It's like a ring of oil around a dry spot in the middle. Exactly what's going on here? What is this mystery force, and why does it repel the oil?
I'm not sure. I'm wondering if it's, I don't know, maybe air or something in the oil that's then evaporating and forcing the oil outwards and upwards. Something to do with heat and what's in there.
I'm not 100% sure myself. I think this is another one where we need some help from the audience. So if you have a clue as to what's going on in Bill's frying pan, could you please email chris@nakedscientist.com or phone up 08459 25 2000 or text in on 07786 20 1960 with your thoughts. Hello and good evening to everyone who's listening to us in Spain on REM FM. You're welcome to join in and contribute too if you'd like to, or if you have any ideas on what's going on. But in the meantime, another reason to give us a call, and those numbers all apply, is if you want to have a go at our teaser. Kat.
We want to know today, what nuclear process powers the sun? Internal combustion or what? Get calling now, 08459 25 2000. Text us 07786 20 1960. Email chris@nakedscientist.com. Couple of right answers so far. Jill in Cambridge, doing quite well. And Jane in Kettering as well.
Sorting out the sparks from the quarks. The Naked Scientists.
Now, we've just been hearing about radiation in your own home, but what about the stuff that actually creates radioactivity, nuclear reactions? Well, it can be used to power our own homes. Earlier this week, we sent the Naked Scientists Anna Loti and Dave Ansell to Sizewell B Nuclear Power Station in Suffolk, which is one of the 19 nuclear reactors in the UK, and currently it supplies around 3% of the UK's electricity needs. They went along with their sturdy protective gear to find out what's inside a power station and how it actually works.
I've managed to get through security and I'm now fully kitted out in blue overalls and a nice hard hat. But before I go and have a look round the power plant, the first question should really be, what is nuclear energy? Well, in the case of the power plant here at Sizewell, it's all about a fission reaction. And to do that, basically, what you have to do is split the nucleus of an atom, like uranium, in two. And this splitting it in half gives off loads of energy. But to find out a little bit more about how that really works, I'm here with Dave. And so, Dave, how do we actually go about splitting an atom in two?
Well, as the name suggests, nuclear energy is all to do with the nucleus of an atom. Now, the nucleus of an atom is made up of two kind of particles. You've got protons, which are positively charged, and they repel each other quite strongly. And you've got neutrons, which don't have any charge at all and just kind of sit there. Now, both neutrons and protons are attracted together over very short range by something called the strong nuclear force. This acts like glue and just sticks neighbouring ones together. This means that very big nucleus, something like uranium, which is the heaviest nucleus you can find naturally, you've got 92 protons which are repelling each other, and that's almost overcoming the attraction of the glue. Now, all you've got to do is give it a little bit more energy by throwing in a slow neutron into the middle of that. Leave enough energy to split into two and break that glue connection. Once that's broken, you've got two halves of a nucleus, which are repelling each other really, really strongly. They fly apart, releasing an immense amount of energy. Now, luckily, it also releases 2 or 3 neutrons, which can go off and hit another uranium atom and split that, and then those produce some more, which can go and split others. And you get a chain reaction, and you can release an immense amount of energy.
OK, thanks for that, Dave. Well, now we've heard about some of the science behind splitting atoms, let's talk to somebody who works with this kind of stuff every single day. So I'm here with Colin Tucker, and he's a physicist and nuclear safety engineer, I think that's right, isn't it, Colin, here at Sizewell. So, Colin, what is it that we're actually looking at here?
You're stood outside the reactor building. That's the big white dome that people see when they walk up and down the coast here on Suffolk. That's 72 metres high. And it makes people think that maybe we've got a big reactor here. We haven't. The reactor's only 4 metres across, and it's buried right down in the basement of that building.
So what kind of energies are we talking about being produced here at Sizewell B?
OK, in that reactor, which is only, as I say, about 4 metres across, we're generating 3,500 million watts of heat. So it's about 1 million electric kettles worth in that small volume. We use that heat to heat water, about 20 tonnes of water a second. We heat it up to more than 300 degrees Celsius. What do we do that for? Well, we can then use that water to heat up some more water at a lower pressure and make steam, about 2 tonnes of steam a second. That travels from the big white building across to the right here into the turbine hall, where it spins our turbines at 3,000 times a minute. At the back end of those turbines are the generators, and that's what we're here for. Nuclear power stations exist to generate electricity, and that's what we do, day in, day out.
That sounds amazing. Can we go and see it?
We can go and have a look at the turbine hall, certainly.
We are now in the turbine hall, and as you can probably hear, it is insanely noisy. What we have is an enormous open building with lots of metal floors around the edge, one of which I'm standing on. And down in the middle is a whole series of turbines. And this is what Colin was talking about. The steam comes into here and it turns the turbines that generates electricity. But we can't really talk in here, so we're going to go outside now and take out our earplugs. OK then, Colin, so now we're outside the turbine hall. It's a bit too noisy to be talking to you in there. How is this different to what's going on, say, in a coal-fired power station? Is there a difference?
Very little difference between this and a coal-fired power station. The steam conditions are a little bit different, and some of the bits of the turbines are a little bit different. But if you walked into a coal-fired station, such as Drax, for example, you'd just see a line of turbines that looks just like these.
So the only difference really is what you're putting in at the beginning. Is it coal or is it going to be uranium?
Absolutely. We just use the uranium as a heat source. That's all it's there for.
So are you pumping in uranium fuel all the time? I mean, are you always constantly having to stoke up the turbine, so to speak?
No, we replace about a third of the fuel with new fuel every 18 months. So we run for 16 and a half or so months continuously at Sizewell B at full power continuously, 24 hours a day. At the end of that, we shut it down, we do a lot of maintenance, a lot of testing and a lot of inspections, and we replace about a third of the fuel.
So I suppose the next question is, what do we do with all the waste? And it's a question that a lot of people are very, very concerned about. So we've got another person here called Matt Lunn. And Matt, can you tell me, what do you do here at Sizewell?
My job is to advise the management about the safe use of ionising radiation and also to advise on the protection of the environment.
Well, it sounds like you're the person we need to be around to make sure we're nice and safe. So we're going to go off now, I believe, to actually see what happens to the waste and where it all goes.
We're currently in the spent fuel building, which is next to the reactor building, and what you're looking at here is a deep pool of water about the size of a five-a-side football pitch. It's about 14 metres deep, and in that pool we've got our spent fuel.
So you just said about spent fuel there. What is spent fuel?
Spent fuel is basically a fuel assembly where we've burnt a certain proportion of the fuel. However, we can't burn the rest because of a build-up of what are called fission product poisons. During the fission process, the uranium splits, and it splits into roughly two halves, and they're called fission products. However, those fission products are actually much better at absorbing neutrons than the actual uranium itself, and therefore what happens is the nuclear reaction will actually die out, and then effectively 96% of the actual usable fuel is actually unburned.
OK, we've got all this fuel left over, and it's in a big pool of water. Why is it that you're storing the radioactive waste underwater? Why is that such a good thing?
The fission products inside the fuel give off intense radiation, and water is a good shield, it's cheap, and it also has a cooling effect as well.
So how does the water shield you from the radiation?
Well, basically, the gamma rays just bounce off of the water molecules and eventually dissipate their energy in the water.
What are you going to do with it after that?
Well, unlike the earlier power stations, our spent fuel is designed to be stored underwater, and we can actually store it here until the end of the station life and beyond, and that's the current strategy. The options for dealing with it in a long term are either reprocessing, like we do at Sellafield, or you can actually just bury the fuel into casks deep underground. Unfortunately, the United Kingdom doesn't have a final repository for spent fuel at the moment. Therefore, we will just continue storing this either underwater or eventually in special casks above ground.
Well, we've now come to the end of our tour of the nuclear power station. Thanks very much to Matt and to Colin for showing us around and getting us past security. But Colin, finally, we're standing now next to the National Grid building, so it's where all the power from the power station goes in to fuel our homes. Do you think that nuclear power is going to be a big contributor to our electricity needs in the future?
Absolutely. At the moment, we generate about 20% of the electricity used in the UK. We're a very, very low carbon emitter in terms of the generation that we produce, and on a large scale. What are we going to do as these power stations get older? We're going to have to replace them with something. To replace them with renewables on such a large scale is going to wreck the landscape. We're going to have some renewables, we're going to have some nuclear. It's a very exciting time to be working in the industry because everyone is now seriously looking at new build again. And I'm sure that in a few years' time we'll see more of these being built.
What do you think at home? If you have an opinion on it, drop us a line, chris@nakedscientists.com. Thank you very much, Anna and Dave, and also to Colin Tucker and Matt Lunn at Sizewell for showing us around this week. Kat.
We've had some new answers in on the teaser. Along the right lines, we have Ian in Rayleigh, Penny in Tiptree, John in Warrington, and from the sunny Costa Blanca, we have Jean in Altea and Eddie in Benalmádena. We also have right answers from Chris in Spain, not quite a right answer from Keith in Watford, and plenty coming in. If you want to answer the teaser, what we want to know is what nuclear process powers the sun?
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
This is The Naked Scientists with Dr. Chris Smith, that's me, and Dr. Kat Arney. And our first guest this evening, Ian Farnan from Cambridge University. Hello, Ian.
Hello,
Thank
Chris.
you for joining us. Now, we were talking about Sizewell there. It's not a very big reactor, 4 metres by 4 metres by 4 metres, they said. That sounds tiny, but huge amounts of radioactive waste, they were saying. How much?
I'm not too sure exactly how much is stored at Sizewell. In fact, all of the nuclear waste that's been produced at Sizewell is still on the site there. So the UK doesn't actually deal with that waste at the moment.
But how much have we got stockpiled? We mentioned earlier there are 19 functional nuclear power stations in this country, and a number have been shut down.
Right. The majority of our waste the volume is 470,000 cubic metres. Now, the interesting thing, or thing that you ought to put that in perspective, is that only a few % of the radioactivity is in the vast volumes there, and that I think 98 or 99% of the radioactivity is in a much smaller volume, and this is what we call the high-level waste. And this is the really, really dangerous stuff.
How dangerous and why?
Well, it emits radiation, beta and gamma radiation. It's extremely harmful. You cannot approach it. It takes many years to cool down. And so Anna at Sizewell would have seen what we call the spent fuel ponds. So when the nuclear fuel rods are removed from the reactor, they're placed in underwater and left to cool for long periods of time. So other reactors leave the rods there for maybe 10 years, 15 years, then pull them out into what's called dry casks, and they're stored outside. But it takes that sort of period of time before you can store them outside of water.
OK, but storing them in the long term, how long are we going to have to store these things for before they're considered safe again?
Well, this is in the UK, we've actually taken a lot of our nuclear fuel rods and reprocessed them. And in that process, you separate out into two major types of waste. You have what's called the fission products, which are the sort of half of the heavy elements, the two halves that are split apart. And then you get the remaining uranium, which is depleted uranium, and plutonium, which is actually generated in the nuclear reactor. And so you've got these two parts, and the fission products themselves are dangerous for about 300 years, one would say. So they have half-lives, the principal elements have half-lives of about 30 years. So 10 half-lives would be 300 years. There are a few other problematic elements in there. Technetium is one, which we'll hear about, has medical uses, but it exists there, and that's quite long-lived. And
some of this waste we've been talking about we say it needs 10 half-lives to be safe, and
yes.
That's 300,000 years.
No, that 300,000 years would be something like plutonium-239.
Yeah, which we are producing in
that's right, and that is so. There's two types of waste.
Yeah,
there's a waste which is what we call the fission products. In the UK, we've separated the plutonium and uranium from the fission products. So the fission products, 300 years. The plutonium and uranium on much, much longer timescales. Now,
so we've got a considerable amount of material that could be radioactive for a third of a million years.
Exactly.
How do we store that?
Well, in July, the government commission called Quorum reported and said that we should build what's called a geological repository. And what they said was that we should dig a hole between 200 and 1,000 metres deep. It'll be a bit like a mine. So a shaft will go down, and then you'll cut out drifts into the surrounding rock, and then you'll emplace canisters of material. Now, in this country...
Does this just mean you put the stuff in a barrel and bury it?
Well, no, the fission products themselves are treated with some oxides, boron oxide and silicon oxide, basically, heated up and formed into a glass. And those are then poured into cans, extremely strong cans, and they're stored at Sellafield, at the reprocessing site.
Now, is that stuff stable for a third of a million years?
That stuff is not necessarily needs to be stable for a third of a million years, because it only contains what we call the fission products. So
but I'm talking about a lot of the stuff that needs to be in the ground for a third of a million years, Ian.
Right. So that material is stored at Sellafield, and we haven't decided in this country what we're going to do with that yet. Well, we've decided what we're going to do with 5%. 5% of that, about 100 tonnes of plutonium, has been set aside as not useful as a future nuclear fuel. So this really depends, Chris, on decisions on whether we build new nuclear power stations and whether those nuclear power stations will then be licensed to burn what we call mixed oxide fuel, which is uranium plus plutonium. So depleted uranium, and then the fissile material will be plutonium.
But what I'm getting at, Ian, is how do we work out a safe way to store that stuff with this incredibly long half-life that needs a long time in the ground to calm down?
Well, what we're trying to do is to develop some mineral-based ceramics, which are then we mix, in a similar way to forming the glass. We mix oxides and we form something which is like a mineral, and there are certain minerals that occur on the Earth which have been proven to hold uranium and thorium for billions of years in some cases. And so those are the sorts of models of the types of materials we want to use. So we would like to isolate these very long-lived isotopes into a mineral before storing it. And hopefully that mineral would be sufficiently durable that it would not decay and then there will not be damaged by the radioactive decay that occurs inside it.
And is that true? Is it?
We haven't found one which is going to last for 300,000 years yet.
How long does it last?
Well, the particular case we looked at recently lasted for about 1,400 years.
So that's a fraction of what you need.
Tiny fraction.
It's a minute amount. So at the moment, what you're saying is we have this high-level waste. We've got nothing we can actually do which we think is going to be a safe long-term prospect for it at the moment. Well,
it's a question of confidence, so that we know this material will degrade under its own internal radiation. Whether that amorphous material will then be dissolved by water is not very well understood.
Why does it get damaged? Why does it fall apart over time? What's going on?
What happens is that there's an alpha particle emitted from the heavy nuclei, like plutonium, and that heavy nucleus then recoils, a bit like a howitzer that's just fired a shell, and that skittles into all the other atoms and knocks them all over the place. And basically, you no longer have a very well-described material, very durable material at that point, because the atoms are all in very high-energy positions, that they're all in, knocked out of their usual positions, and so can be attacked more readily by water.
So the challenge is to find something stable. We've had a suggestion here from Keith in Watford, who says nuclear waste could be encased in glass, put on top of a rocket and shot into space. And is there any sensible way of disposing of nuclear waste that doesn't mean basically putting it in the bin on the planet?
Yeah, David in Chelmsford says, can we not dump it on the moon?
Right. Well, I think the Committee on Radioactive Waste Management, which just delivered its report last July, did consider very quickly putting things in space. Firing them into the sun is another option. And a feasibility request went to NASA, and they could only guarantee, I think, 1 in 35 launches wouldn't result in an explosion. Right. So the idea is it would be too dangerous to to do that because of
Which
possibilities
would
of
be devastating
launchpad explosions, yes.
It would be similar to what happened with Chernobyl, basically, wouldn't it? I mean, the amount of contamination.
It would be, you would deliver it into the stratosphere and it'd be spread around the world, yes.
That just sounds terrible. So you just say more research really is needed quite urgently.
I think the research that's being done is to really research the materials that we put these things in. We actually form into another material. And that material is actually then very, very durable with respect to water. And the main problem is that if you put this stuff down deep into the ground, the question is whether that material will come in contact with water. That's the only way that the radioisotopes will leak out, is if that material comes in contact with the water. So that can be controlled by the geology of where you put it, or it can be controlled by the material itself. And you obviously need a combination of those two. But the better you can make the material in the first place, the more certainty you have in the disposal process.
What's the situation in America? Because they've invested quite a bit of money, haven't they, in deep burial?
That's right. Well, they have a repository site in Nevada. It's about 90 miles west of Las Vegas. And all the states in the US have basically agreed, except one, which is Nevada, that the US
funnily enough
nuclear waste should be sent there. And at the moment, there is one legal challenge which is preventing the go ahead of that project. But they will have lots of nuclear waste from their nuclear weapons program and from their commercial nuclear generation program, which will be transported to Yucca Mountain and be set in a type of repository which I just described earlier, which will be dug out with what we call drifts.
I was writing a blog last year for the Institute of Physics looking into sort of nuclear energy and those kind of issues. And it did seem to be there's a lot of discussion about the right way to build nuclear power stations or not and how environmentally friendly it is. But no one seems to have really solved what to do with the waste. Anyway,
the question is, if you ask most scientists, I think, who work in the area, we have a gut feeling it'll probably be okay. But that is not good enough.
The Naked Scientists with Dr. Chris, Dr. Katz, and we're talking this week about the science of radioactivity, and now we're going to talk about the science of radiology from Adam Brooks Hospital in Cambridge. Here's Anand Krishnan. Hi, Anand. Thank you for coming in.
Hi, Chris.
Now, you're a radiologist, which means you use radiation for medical purposes.
That's right.
It must make a big difference to doctors' lives.
Absolutely, because it helps with both the diagnosis and treatment of disease, and it's revolutionised the way things are going, and it's only going to get better now.
But they're quite dangerous, though, aren't they, X-rays?
You would think so, but it's about using it responsibly. And if I can just put it in perspective, if you have a chest X-ray, the lifetime risk of developing a fatal cancer is less than being killed by a bolt of lightning.
But, I mean, can you put some figures on it in terms of how much excess radiation I'm getting through having a chest X-ray? Because some people say it's things like it's the equivalent of going out in the sun for 3 days or something.
It's getting about 10 days' worth of background radiation.
But that's a simple chest X-ray, isn't it? So
yes.
What about when you have more complicated procedures? Abdominal X-rays or CT scans?
Well, CT scans do give more radiation, but you have to balance the benefits versus the risks. And even then, if I use the same analogy as before, it's having an abdominal CT would give you the same lifetime risk of developing a fatal cancer as dying from an accident at work.
How does an X-ray actually work? So when we want to look at someone and image their internal organs, how does this work?
Well, first of all, we create the X-rays by accelerating electrons at a metal target, and that interaction gives off the X-rays, and we can then target that at the part of the body that we want to image.
Because X-rays are a form of light, aren't they? Just a very short wavelength.
Yeah, it's part of the electromagnetic spectrum, so it's a different part of the spectrum. So what we do is we target it at the body, and it can do one of two things. It can either go through or it can interact with the tissues, either the soft tissue or the bone. And it's the X-rays that go through, and then we can detect that on the X-ray plate, and then so we develop a shadow image of what's actually going on in the body.
So some bits of the body mop up the X-rays more than others.
Yes.
This is what gives you an image.
The heavier atoms tend to absorb more of the X-rays. So bone, obviously...
Lots of calcium.
Yes.
Yeah. So what about when you want to do more complicated things? Because obviously an X-ray is just literally zapping someone straight through. But what about when you want to build a three-dimensional picture with, say, CT? How does that work?
Well, that's using the same sort of thing, except that you're firing X-rays from different angles, and then that's being then picked up by a computer so that you can get a 3D reconstruction. But everyone talks about X-ray and CT, but radiology also uses non-ionising radiation as well, so ultrasound, MRI, and so these are much safer forms of radiation as well.
We've had a question in here from Maggie Ilkshall in St Andrews, and she wants to know, what is the smallest thing you can detect in the body with an MRI or a CT scan? Is it 10 millimetres? Is it smaller? What's the smallest sort of dangerous thing, say a tumour, that you could pick up?
The resolution of MR is in millimetres. Obviously, if you wanted to go further with CT, you could, but you would be giving them a far greater radiation dose.
I mean, there's also some people that suggest that maybe everyone should have a whole body CT scan every year. I think some people in America do. Is that a good idea?
I don't actually think so, because that, again, you're looking at giving someone a radiation dose, and it's not without its own risks, as it's been made quite clear today. So we have to look at, do the benefits of doing the test outweigh the risks of getting something as an adverse effect?
Anand, we've got a quick question first. Margaret in Corby wants to know, how does something like radiotherapy treat prostate cancer? Because you've talked about using these things to take pictures of people, but how do you actually use this technology to damage bits of the body?
Well, there are three ways of using radiotherapy. One is something called external beam radiotherapy, where X-rays are fired at a target. Another way is brachytherapy, where a radioactive source is put, say, in a tumour. And a third way is, say, injecting radioactive substance like, say, radioactive iodine, which treats thyroid cancer.
Why does it damage the body and just the tumour? Or the tumour mainly?
Because of the way that it interacts with cells, because it causes DNA damage. It's specifically the ionising radiation that we use, because what happens is that the interaction with a cell causes electrons to be given off, and having cells which are ionised. Usually when X-rays or gamma rays interact with the body, they actually interact with water, and that water can form free radicals, and the free radicals can cause damage to the cells through damaging the DNA.
So Naked Scientists with Dr. Chris and Dr. Kat. We have run out of time, but thank you very much, everyone, for having us in your living rooms and in your cars this week. And thank you also to our production team, Anna Lacey and Petro Minch, for doing a great job. Thanks, Dr. Kat, and also to our guests this week, Ian Farnan and Anand Krishnan. Now, next week, we're devoting the entire show just to tackling your science questions. So if you want to know how many pieces of toast you can make with the energy in a lightning bolt, why food turns brown when you cook it, and also why wasabi makes your nose run, or you'd like the answer to something totally different, or you just want to say hi, then please send your questions to me now, chris@nakedscientists.com. In the meantime, you might like to give the Nature podcast a listen for more up-to-the-minute science discussions. That's at nature.com/nature/podcast. And don't forget, the Naked Scientists Forum is a thriving nucleus of social and scientific intercourse and is well worth a look. That's at nakedscientists.com/forum. Thank you once again for joining us, and until next time, goodbye!